Alright guys, so this is time for a new video, alright, for Math 60, keeping on with Math 60 program. Alright, so in this video we begin a new chapter, chapter 7 on radical expressions, radical functions, rational exponents, right? Essentially, very similar ideas as we have done in the past, right, with exponents, but in this case for far as exponents, we are going to have exponents that have rationals, right? In the previous chapter, in the previous few chapters, we were working with expressions that have uh, what they call the integers as exponents, right? As an example, let's see, we have something like, I don't know, x squared plus 5x cubed, right, plus 7x to the fifth power, right? These powers, these exponents right here, the ones I'm highlighting here. Okay, those are integers, right? In this chapter, we're going to look at expressions that have x to the 1/3 plus x to the 1/2, right? Different types of exponents, right? In this case, rational exponents. Okay, so that's what the chapter is about. But first of all, we need to define what the square root is. And by the way, you may have you may have an idea of what the square root is, right? So the square root, right, principal square root is the number b is the square root of a if b squared equals a. So that's the formal definition, right, of the square root. However, for example, when we want to find the square root of 49, right? So we ask ourselves what numbers squares are equal to 49, right? So in a way, the number 49 has two square roots, right? One is -7 and +7 is the other one, right? Why is that? Well, because both -7 squared equals 49 and +7 squared equals also 49, right? So it might be a good idea to list the first few perfect squares, right? So let's go ahead and do it on the side, right? Like we don't have to do all of them, right? Just a few. 1 squared equals 1, 2 squared equals 4, 3 squared equals 5, no, not 5, actually 9, 4 squared equals 16, 5 squared equals 25, 6 squared equals 36, 7 squared equals 49, as we have seen earlier in the definition. 8 squared equals 64. 9 squared equals 81. 10 squared equals 100, right? And 11 squared equals 121. 12 squared equals 144. All right, let's keep listing a few more. All right. 13 squared equals 169. 14 squared, I believe, is 196. And then 15 squared equals 125. All right, I think that's enough. We don't have to do all of them, right? Maybe the other one, a very common one, 20 squared equals 400. 25 squared equals 625, right? Okay, so let's keep going. Let's with the definition. So the notation for this is the square root of 49 equals 7 because 7 to the second power equals 49. Okay, so that's how we go with the notation for radicals. Okay, a very important remark that we need to keep in mind is that the square root of a negative number, it's not a real number, right? In fact, this gives rise to the imaginary numbers and then the complex numbers. However, that's not a section we cover anymore, right? But it's good to know that every time we have the root, at least for the scope of our course, the square root of a negative number will not be a real number. All right. So, what are the properties of square root? So, number one, okay, every positive real number has two square roots, one positive and one negative. It is very important to know as well the square root of 0 is 0, right? This symbol right here, right, it's called the radical sign, right? More completely, it looks more like this, right? And the quantity inside of the number or algebraic expression under the radical sign is called the radicand, right? It's called radicand. Okay, maybe not this color, maybe blue. Okay, it's called radicands. Okay. All right, speaking of the first property A, when you look at the homework, you are going to have questions like the following. What are the roots of okay, we already did 49. Let's do another one. Let's do, I don't know, 64. Okay, let's do 64. What are the roots of 64? When you see the question like this, right? Okay, let me call this letter A. Okay. Let me call that a letter A. Okay, so the roots, notice roots, plural, right? So we're looking for two numbers that square are 64. Number one is -8, comma, and 8. Okay, so there are two answers to this question, right? So depending on how the question is worded, right? If you are explicitly asked in words, what are the roots, right? However, if you are given evaluate the square root of 64, right? In this case, they are only asking you for the positive one, right? In this case, let's highlight this part, right? In this case, the non-negative square root is called principal square root, right? In this case, they're asking us for what we call the principal square root, okay? The one that is only the positive one or non-negative, right? Non-negative, positive, right? So you will see on my MATLAB the different ways the question is worded, right? Okay, so let's go ahead and do more examples, all right? So the first example, the square root of 36. In other words, what number squared equals 36? So on the previous page, we were looking at the first few squares. So in this case is 6, right? The final answer to this is 6. And this is because 6 squared equals 36. All right, that's why. Letter B, the square root of 9 over 16. Okay, so in this case, take the square root of both the numerator, which I'm highlighting, and the denominator as well, right? We need to take the square root of both numbers. Okay, so in this case, square root of 9 is 3 and the square root of 16 is 4. Final answer. And this is because 3/4 quantity squared equals 9/16. In other words, it takes us back to what we have over here, right? Inside of the radical, which is the radicand, by the way. Okay. Now, let's see. What about when we have decimals? Okay, so up to this point, we are not allowed to use any calculators, right? However, we need to rewrite this number in fraction form, right? Because there's no way, well, unless you have some a good number sense, right? Yes, you could do it right away. However, if you look at a decimal, don't know how to do, right? For example, look at the number 0.25. We know 25 is a perfect square, whose square root is 25. However, we don't have the number 25, but the number 0.25. So let's write that number 0.25 as 25 over 100, right? That's the same as 2500, right? Because this 0.25 goes to the tens and the hundreds, right? And everything under the same radical. Now let's take the square root of both numbers, 25 and 100, right? So square root of 25, which is 5, and the square root of 100, which is 10. In this case, as opposed to the previous examples, well, in this case, we can simplify this fraction to further terms, right? So this will be 1/2, right? Which is the same as saying 0.5, right? And the reason why this is the square root is because 0.5 squared equals 0.25. All right, and that's final answer. All right, what about when we have variables, right? What about when we have variables? Okay, so the square root of x to the 6th power, all right? So let's do the explanation first, right? So because x to what power equals x to the 6th? X to the what power squared, right, equals x to the 6th, right? So in this case, what's the missing power here, right? There's a missing power here, right? In this case, it's x cubed, right? So the final answer to this is x cubed, because x cubed square, right? In this case, we multiply the powers. 3 times 2 equals to 6. All right. Let's do the same on the next example. Okay, so we take the square root of 9 and the square root of x to the 12th power. The square root of 9 is a nice number. That's a 3. The square root of x to the 12 will be 6. Why is that? Well, because what quantity squared equals 9x to the 12th power? All right. Okay, let me change this to a different color. Okay, to the same color, x cubed. In this case, the quantity 3x to the 6th power. All right. So in this case, when we square both numbers, right? If we square the 3 and then we square the 6, right? When we square the 3, we get the 9. And when we square x to the 6, we multiply the power. 6 times 2 equals 12. All right? So that's why final answer. All right, let's look at letter F. Okay, letter F. Negative square root of 81. So let's ignore the negative sign for a second, right? And focus only on evaluating the quantity with the radical. So the square root of 81, what's the square root of 81? Square root of 81 is 9, because 9 times negative 9 equals 81. However, the negative sign is outside of the radical, that just gets squared, all right? And in this case, the explanation is because negative squared equals 80. $81, all right? In this case, the quantity 9, all right? Actually, we can just get rid of the negative sign, right? Because we're only looking at the number, right? So this is 9, all right? Okay, what about the square root of negative 1? Be careful here, all right? In this case, the answer to this question is not a real number. And that's because we cannot take the square root of, we're not gonna take the square root of the a negative number, all right? Okay, so let's move on to the next topic, finding cube roots, all right? Just the same way we define the square root as what number squared equals the number inside of the radical, right? That is the radicand. For cube roots, we're looking for example, if we want to find the cube root of 27, right? We are looking for what number cubed equals 27, right? So in this case, what number to the third power equals 27? So in this case, the answer to that question will be 3. All right, and let's list a few perfect cubes. Okay, of course, I'm going to start with 0 cubed, which is 0, and then 1 cubed, which is 1, and then 2 cubed, which is 8, and then 3 cubed, which is 27, and then 4 cubed, which is 64, and then 5 cubed, which is 125, and then what else do we have? 6 cubed, which I believe, let me find out what that is. 6 cubed, I believe is 2016. Yes, it's 216. And 7 cubed, which is 343. That's enough. We don't have to do all of them. Maybe we jump to 10 cubed, which is 1,000, right? That is multiply 10 by 10 times 10, that's 100 times 10, 1,000, right? Okay, so let's make a distinction here with the square roots. As opposed to the square roots, we can find cube roots of negative numbers, and the result for that is a negative number, right? The cube root of a negative number is a negative number, and we will explain that soon on the next examples. Okay, let's look at the first example, the cube root of negative 64. In other words, what number to the third power equals 64? In this case, okay, the cube root of a negative number, bring down, carry on the negative sign, and evaluate the cube root of 64 as if we didn't have a negative sign, but in this case we have it. So the answer to this is 4. And that is because, right? Because negative 4 to the third power, right? It's going to be equal to negative 64. How come? Okay, you might want to write to expand all this, right? -4 times -4 times -4. That's what -4 cubed means multiply the same quantity by itself. Okay, first of all, multiply the numbers. 4 times 4. Okay, let me highlight what I'm doing. 4 times 4 is going to be 16, and then 16 times 4, it will be back to 64, which is what we had initially, right? 64. However, let's multiply the signs. Negative times a negative equals positive, and then positive times a negative is negative in this case. All right? So that's why. All right, let's look at the next example. For the next example, we take the cube root of the number 8 and the cube root of the number 125. In other words, for the numerator, what number to the third power equals to 8? In this case, as we listed it above, it's 2. And what number to the third power will be equal to 125? In this case, we say 5. All right. And this is because two-fifths to the third power equals 8 over 125. Okay, that's why. Okay, what about when we have variables in this case? All right. So the cube root of x to the 6th power. All right, so in this case, we are going to have as a final answer x squared. Okay, why is that? Well, that's because, okay, what quantity cubed equals x to the 6th power? Well, the quantity x to the 2nd power cubed equals x to the 6th. Again, keep in mind that these two numbers that I'm highlighting, right, that I'm highlighting in yellow, right, these two numbers multiply. The power of another power, we multiply the powers. 2 times 3 equals 6. All right, let's do another one. Okay, so first, let's do the explanation. Why not? Okay. What quantity cubed equals 27x to the 15th power? All right. Okay, the number, I guess it's very straightforward, right? It's what number cubed equals 27? That's 3. X to what power equals 15? Okay. In this case, 5, because when we multiply 3 times 5, right, we get 15 as a power. Okay, so final answer, 3x to the 5th power. All right, so far we have looked at square roots and cube roots. All right, so now can we extend this concept to any further root, like the 4th root, the 5th root, the 7th root? The answer is yes. All right, and we can generalize this idea, right, by finding what we call the nth root, right? Nth root could be, again, the 5th root, the 7th root, the 11th root, the 27th root. Yeah, so we can look at all of those, right? Okay, so two things to keep in mind when finding roots that are higher order, right? So one thing to keep in mind, the number one thing to keep in mind is that if n is odd, right? That is, if we're looking for the cube root, okay, or the 5th root, or the 7th root, or the 9th root, right? The radicand, right, the number inside of the radical, right? We can have any number inside, positive, negative, 0, right? So for odd roots, this is not restricted at all, right? As opposed to the fact that if n, the index, is even, right, then the number inside of the radical, right, that is the radical, has to be a positive number. Otherwise, if we have a negative number and the index is odd, right, I mean the index is even, in this case we have the fact that it's not a real number, right? So what about the index? Notice I mentioned something called the index. So this quantity I'm circling, right, this n is called the index of the radical. And that's what is going to tell us what to do, right? That's going to tell if you have a square root, right? When we don't have anything, right? Square root of x, for example. Notice nothing is written. This is understood to be a 2, right? That means square root. Unless you have the number 3, that means cube root, or the fifth, or the number 5, fifth root, or the number 4, the fourth root, etc. All right, let's evaluate. Let's do a few examples. Okay, let's simplify the following expressions. All right, so in this case, let me highlight the index, right? The index is the tiny number that we have here. Notice in this case is 4, right? So in this case, we have the fourth root, okay? So the fourth root of 81. In other words, we're looking for the number, right, that raised to the fourth power would give us 81. In this case, that number is 3. Be careful in this case, right? Be careful with the number 81, because the number 81 is both a perfect square and a perfect fourth, right? If the question were, what is the square root of 81? Well, the square root of 81 is 9, because 9 times 9 equals 81. In this case, we're looking for the square root of 81, I mean the fourth root of 81, and the answer is 3, because 3 to the fourth power, which is 3 times 3 times 3 times 3, equals 81. Okay, that's what we're doing. Okay. Okay, let's look at the number, the fifth root, right? Okay, let's highlight the index. In this case, the index is 5, right? So we are looking for the number that raised to the fifth power equals to 143. All right. However, notice we have a negative number, right? Notice we have a negative number. I'm highlighting the sign for you so you can check it out, right? Now, in the case in which the index is odd, right? Okay, let's point that out. Index is odd. In that case, we can take the fifth root of a negative number, and the answer to that is negative, right? Again, let's go up here, right, to the sentence highlighted with purple. If n is odd, then the radicand can be any number, right? And the final answer is we carry the negative sign, and we look for the number whose fifth power is 243, and in this case is 3. All right. So negative 3 is the final answer, and this because negative 3 to the fifth power equals, which is negative 3 times negative 3 times negative 3 5 times equals negative 243, right? All right. Let's see. Let's look at the next one. Okay, number one, the first thing you identify every time you have a radical expression, look at the index, which is what I'm highlighting here, right? In this case, the index is 4, right? The index is 4, and this happens to be even, okay? So let's write that down. Index is even, right? And in this case, when the index is even, that is like the square root, like the 4th root, like the 6th root, the 8th root, the 10th root, the 12th root, etc. All the even indices, right? In that case, we need to be careful because those even indices cannot take negative numbers. So in this case, the answer is not a real number. All right, so that's the answer to this, not a real number. Okay. Letter D, let's look at the cube root of 64x cubed. All right, so let's highlight the index, right? The index is, in this case, this tiny number, in this case, 3rd power. So the cube root of 64x cubed, all right? So what quantity, okay, what quantity to the 3rd power equals 64x cubed? So first of all, what quantity to the 3rd power equals 64? Well, as we listed them earlier, right, the number that works is the number 4. Okay, so 4 to this 3rd power gives us 64, and then x just to the 1st power, right, equals x cubed, right? So final answer is 4x. And this is because for x to the 1st power, right, equals 64x cubed. All right. So that's just to get a feel of what roots are, right? So maybe the most common one is the square root, right? The easy one to memorize, right? By just keep in mind what the perfect squares are, right? And then we go with the cube roots, and then this concept can be still extended to any kind of root, like the 4th root, the 5th root, the 7th root, etc. Okay, let's move on to looking at functions involving radical expressions, right? So to that end, right, all we do as usual, plug in the value of x and simplify. In other words, evaluate. Evaluate means plug in, then simplify. All right, so in this case, we have two functions, right? We have the function that I'm highlighting with pink or purple, f of x, and green, which is g of x, right? We have two different functions. One is f of x and g is, one is f of x and the other one is g of x. All right, so for letter A, they're asking us to input x equals 8, right? input x equals 8, right? So plug in 8 and minus 4, subtract 4, right? So 8 minus 4, in this case, we have the square root of 4, and that's a nice number. The square root of 4 is just 2, all right? So I'm gonna highlight this f with purple right here, just so you can see which function we're gonna use, all right? And by the way, this is called the output. Remember input, output, our definitions back from functions, right? So let's do g of -1. In this case, they're asking us to plug in the green function, right? Okay, so in this case, the input is x equals -1. That's what it means, right? And this will be the cube root of -1 plus 2, right? We are using the second function, right? And that's going to give us 2 minus 1, or -1 plus 2, that's a 1. And the cube root of 1 equals just 1. All right. Okay, let's look at the other examples. Okay. F of 6. In this case, the letter f right here is indicating that we should use the first function, f of x, right? In this case, the input, right, will be x equals to 6. Okay, so plug in square root of, replace x with the quantity with the number 6, and then subtract 4. Right? So 6 minus 4 equals square root of 2. In this case, we're going to leave it like this because we don't have a perfect square root. Unless you use a calculator, right, you're going to get decimals. In this case, we're not going to do that. We're going to keep it in radical form, right? If we had a number that had a perfect square root, for example, then we would take the square root, like for example, like in the first case, we got a square root of 4. In this case, we go a bit further. For square root of 2, we just keep it as square root of 2. Okay. Now, g for letter D, they're asking us to evaluate g of 1. Okay, so in this case, the g is indicating that we are using the function in green, right? The one with the cube root. Okay, in which the input is x equals 1. All right, so the cube root of 1 plus 2. All right, and this will be the cube root of 3. All right. And that's about it. That's one example of evaluating radical functions. All right. Now the next part will be recognizing the graphs of a radical function, right? So the square root function, right, it's going to look like this, right? It's hard to draw, right? It's not easy to draw here in the tablet, right? And the cube root looks like this. Okay, let's identify the domain and the range of these two functions. Domain. The domain again starts at the leftmost point, right? In this case, 0. And look at the arrows again. Remember the trick for finding domain and range from graphs, right? You might want to split that in 2. This goes from 0 to infinity. All right. The range, on the other hand, and it's going to be the same. It's going to go from 0 to infinity. All right. Again, for range, we go from the smallest value of x all the way up, right? What about the cube root function, right? The cube root, okay, domain and range. Okay, domain and range. Okay, notice this function as opposed to the square root has two tails, right? And the endpoint, you might want to use the trick again, right? Of writing it like this. Notice in the x direction, the graph goes on forever on either side, right? So the domain will be all real numbers, or negative infinity to positive infinity. And the range, likewise, will go from negative infinity to positive infinity as well, right? Look at the arrows, one pointing down, right? Let me highlight that. One is pointing down, the other one is pointing up. That is, the domain is all real numbers in the vertical direction. Just the same way as in the horizontal direction, right? This means it's going on forever on either side, right? All right, guys, so that's it for this first section. We will see again in the second section, 7.2. All right.